everyone to the Friday Think Trees virtual webinar and our last presentation of the day and of the conference. Um, Before I start, I wanted to make a comment. Somebody had asked about the CEUs for the last presentation. The screenshot wasn't up very long. The easiest way to get that information is just to go into the archive sessions, pull that video up and zoom down to the end of it and pick up that information that you might need. All right, well, it's my pleasure then to introduce our next speaker, David Kelly. David Kelly is the president of Kelly and Associates Environmental Services Incorporated. He's a plant and soil scientist who has been involved in wildlands ecological assessment and habitat restoration, as well as agricultural and urban soil projects for over 40 years. He picked up degrees in zoology and botany at Texas Tech University and almost finished a PhD in plant physiology and soil science at UC Davis on his way to starting his consulting firm in 1981 in Davis. Although David maintains he has never had a career track job, he has managed to spend time as a roughneck in the West Texas oil fields, teach upper division plant physiology at UC Davis and wildland ecology at Humboldt State University, grow and export a few tons of asparagus from Peru, design and permit what was at the time the largest wetland mitigation project in the US west of the Mississippi, and testify and provide consulting services as an expert on wetlands, soils, trees, and agricultural issues in Hong Kong, West Virginia, Hawaii, Belize, Mexico, and throughout California. He also enjoys spending time hunting and swimming across most of the US. Along the way, he has served as an officer in the Soil and Water Conservation Society, the Society for Range Management, Professional Soil Scientists Association of California, the California Native Grasslands Association, and other professional organizations. And he has had the privilege and pleasure of teaching way too many courses on soils, wetlands, agriculture, and trees to resource professionals in several states. He brings a real and long-standing interest in the conservation and management of natural resources and the complex realities of trees and soils to our Think Trees conference this year. He can be reached at dbkelly@jps.net. David Kelly, the floor is yours.
Thank you. I don't, there's not much left to say, I guess, so that's good. Can you hear me?
Yes.
All right. I'm gonna shut my screen down just a bit, 1 second there. Okay, great. Well, thank you for the invitation to give this talk. Thank you very much for providing a great list of speakers ahead of me, especially the last one. Holly covered a lot of material that I was actually intended to cover, but it's going to be a different soils presentation from probably any that you've ever heard, unless you've heard me speak. I really pay attention to soil geomorphology, which is landscape. What this, well, let's see. What this webinar is about is dirt. And I'm thinking that the best thing, I'm having a little trouble finding me there, so I get it. All right, there, I'm gonna leave it at that. First time for me giving a big webinar like this, so very well. Well, there's another word for dirt, a few more words for dirt. How about soil biochemo physical geomorphology? How about pedo-eco-biophysico chemical geomorphology? Or as I like to say, my approach is soil landscapology. And I use these not really in a way to be flip. I use these because when you look at a soil, these are the elements that you're looking at. The ecology of a landscape, the biology of a landscape, the physico-chemical qualities of a landscape. If I don't get anything else across in this whole webinar, I want to get that across, that what soil is a reflection of the ecological processes, the ecosystems that are at play in your landscape, whatever landscape it is. This applies, by the way, not just to arborists, which I spend a lot of my time working with trees, tree roots, and soils, but also to archaeologist, orchardist, any kind of urban landscape person. It's across the broad spectrum of natural resources that we actually find a sort of a baseline, a real baseline in soils. Let me think. Okay. I put this sort of in my introduction that soils are a really diverse and dynamic baseline ecological component of terrestrial plant growth. Again, I have spent a lot of time on urban soils. I spent a lot of time in orchards. I spent a lot of time on ag soils, on wildland soils. I find that understanding soils of any of those systems and any of our natural resource systems is really the baseline for site assessment, for finally for making management decisions, tree management decisions in particular. A very important part of our almost ignored ecosystems or ecological processes spectrum is the soil component. And again, that's what I'm going to try to get across in this map. One thing I would mention, I'm really interested in several things that go on in the landscape, but particularly in the landscape industry, whether it's agricultural, urban, wildland, or whatever. One of the things that we try to do as natural resource scientists is figure out what are the questions attached to a landscape when we're making a decision. One of the first things we have to recognize is that what works here doesn't necessarily work 10 feet away or 100 feet away or a mile away. And I think that's really important to understand this diversity issue. I'm going to illustrate that with slides. There are many mythologies, and I actually was exposed to them, as you all were in Holly's talk, concerning soils, and particularly soils and plants, but soil and tree roots in particular. I'll hit some of these as we go through this. I think it's important to understand that the mythologies, and for that matter, some of the science, doesn't really hold as you go from one landscape to another, and we'll get to that again in illustration as we go through this. I was happily watching Holly discuss the compaction issues. She didn't really mention something I always add to compacted soils, which is stratification or stratified issues. A soil that's been displaced in any way and becoming another soil is going to have a compaction problem. It just comes with the territory when soils are moved around. As it turns out, and probably just as important, is the stratification that occurs when a soil is moved, or a soil material is moved from one place to another to make it become a soil or to put it to a soil resource use. There's a real tension here in most projects, whether it's agricultural or engineering, or for that matter, with landscape architects, is that the tension is that what I want to do as a grower of plants, as a horticulturist or an orchardist or an agronomist or an arboriculturist, I want the roots to be able to make their way through the soil. The engineers don't like that, okay? They want the roots to not go through the soil, or at least they want soil in such a condition that it's hard for the roots to go through. And that tension is one that has me sitting in big meetings and big corporations, a lot of time with 30 people around the table, hollering at each other about 95% compaction, you're crazy. We've got to do less than 90 in order to get the roots to the soil. In fact, we got to get down to 85, and we're going to spec an 85% compaction on this project. I'll get into that a little bit more too. It's all in good faith, and everybody's trying to do the best they can for their client. But it's one of the tensions that you're never going to escape if you're working in development and agriculture in particular. Lastly, I'll get to a little bit of some of the projects that I've had where I actually put things in place in order to hopefully make things grow, particularly trees, but also grasslands, shrublands, various other wildland and rangeland vegetational components. It's the fun part of what I do. So basically, what I want to do today is kind of celebrate all these ecological processes. We're going to look at landscape stability. We're going to look at age. We're going to look at the dynamics of age and landscape stability. We're going to look at the magnitude of some of the processes that affect soils or affect the production or the genealogy, excuse me, the genesis of soils. And I'm almost at the end of almost everything I have written down for this whole talk. The rest of the stuff's going to be pictures. So enjoy. I think what you're gonna get is a tour at first of many of the world landscapes that I've been involved with or know about or have dealt with. But there is something that ties together every place in the world, and that's that there are these at least 5 factors in front of you right now that are determining what the soils are going to allow the plants to do, what the soils are going to, how the soils are going to behave, what they're going to be doing with regard to their role in the landscape. This particular slide is, if you might notice, the graphics look kind of old. It actually came from a man named Hans Jenny. He was a professor at Berkeley, at UC Berkeley. He was a little Swiss guy, if I'm not mistaken. I met him once at his office. He wrote a book in the 1940s, 1941, on the factors of soil formation. And to distill that book into this slide is kind of interesting, but historically, we as soil scientists look at the things that affect soils, affect the development of soils in the landscape. The things that we can actually identify that are factors in an integrated soil equation, if it were, as it were, are climate, the biological activity in organisms, the topography, or where or how in the landscape the soil surface is oriented, which includes slope and aspect and things like that. What the parent material is, which is actually what the soil particles themselves are made of, and where they came from, which is also very important, whether they're weathering in place, whether they've been moved around in the landscape. And the hardest thing to discuss is time, how long it takes for these kinds of things to develop into a soil and take all the different components of these soil forming factors. And I'm going to spend quite a bit of time on this in pictures, how they get to a point where we can actually call something a soil. How do these various sediments or rocks, for that matter, become a soil? One has to explain or understand all of these things. And lastly, if you actually are looking at a soil, you've got in front of you a record for that particular place in time, in the landscape, of all of these different things that have acted on those soils or acted on the materials that became those soils. Again, if I don't mention these different factors as I go through this talk, I'll be failing you, because I think that each one of these, once you understand some of the dynamics of that particular place in time and in location, you're going to begin to understand a little bit about why, once you understand soils, and once you do an assessment of the soil factors there, the soil forming factors, you get an idea for what the capability of those soils are. That sounds all highfalutin, but you remember how highfalutin I got with those long words describing these factors in 1 or 2 words. Now we're going to see some pictures, so I'll leave it at that. Let's see if this works here. Yes. Okay. Just to mention again, these things that we just discussed. Time is a factor, how long it takes something to happen, what the parent material, that is to say, what the rock that became a particle or became weathered enough to produce a smaller particle that could then interact with all these climatic, topographic, and organismic or biologic issues. That's something we need to really begin to think, this is how we get at understanding this place in the landscape. Okay. Most of you would recognize this as a relief map of the United States, and that's solely what it is. It's got some interesting coloring for me anyway, because as a soil scientist, I'm wondering, well, I wonder if that green in this, let's say the Mississippi Valley, or the green of the Appalachians, is that a different parent material of soil? No, actually, it's just an artist's rendition of the slopes in this relief map, but it also is an indicator of, among other things, climatic differences. and among other things, amount of water in that system in those various places. We're over here. I don't know if I can, yeah, I've got a little cursor here. We're over in New Mexico, right in here. I'm going to be talking about places that I've worked in New Mexico, down here close to the border, a couple of places up in the Clovis area, a couple of places in Santa Fe, spent some time in Albuquerque. So I've been around. I grew up and went to school in West Texas, right across the border, right over in here in Lubbock, and have spent a lot of time kicking around what I consider to be kind of my heart's country, the arid west of the United States. I think we're going to see a lot of examples of that. I'm just going to keep going on here. Relief is one of those components. The topography of the ecosystem provides a lot of material. Here's a watershed assessment from the San Joaquin Valley of Central California. If you look at this kind of, it's fuzzy on my screen, maybe it's just because it's been expanded too much, but nevertheless, think about a watershed concept. Watershed is a ridge to ridge. It's a drop of rain falls here. Where does it go? It goes here or here or here. Well, that's a watershed right here. And if you look at these rolling hills, you actually see a watershed after watershed after watershed just across this system. Okay, the point simply is that each of those watersheds has its own slope and aspect characteristics. The surfaces, the soils, have different exposures to sun, wind, and moisture, and temperature for that matter. So think about it for a second. If the sun shines basically in the south, which would be in this photo to the left, onto the system, those slopes that are exposed to the sun, that are insulated, that is, they get a lot of sunlight, they actually are subject to drying out, that the slopes on the north side of those slopes, the north side of these watersheds, sorry, the north exposure of these watersheds, those are going to be more mesic, that is to say, better watered. They're going to be cooler, and they're going to have a completely different place for plants to grow. This just go down valley a little bit, and this shows in this particular picture, looks like it was taken in, oh, I don't remember, March or something, in the Central Valley. Oops, let me go back there. Oops. Okay. Again, illustrating just what I said, a southern exposure of this slope means it's drier and hotter. A northern exposure of this slope, here's the north is this way, south this way. Okay, much wetter. And at this particular time on those grasslands, the vegetation actually reflects what the soils are doing, how much soil moisture is there, how much heat is there, how much heat accumulates. All of a sudden, in this particular very, very small watershed, I get an idea that the soils on one side of it, on the right side, say, are going to be perhaps hotter, perhaps drier than the soils on the left side, cooler and more moist. And the vegetation says, yeah, David, you're right, because you can walk at certain times of the year in our annual grasslands of California, up and down these valleys and see the same thing. And in fact, it's exposed, it's in much greater degree. You see that with shrubs and trees in most mountains and all over New Mexico. I was just, when we were having our clinics in Portal, Arizona, right on the border, we were looking at exactly these exposures in the Chiricahuas. And you'll see that anywhere you go where there are mountains, even in that humid east where you get rainfall all the time. We happen to be getting rain today, but it's a good thing. Okay, if you talk about parent material, you have to talk about rocks. And I'm not going to go into the geology of New Mexico. Actually, Holly covered a lot of that very well. But the parent material does get expressed in the soils. Parent material being the source, the rock source that becomes an eroded and sedimentary deposit somewhere for materials that become soils. So if you've got an alkaline substrate, an alkaline rock, you're liable to have some basic soils, basic pH soils. If you have acidic, the same thing. You're going to carry some of those characteristics. In addition, this is where we start thinking about salts and salt production or salt accumulation in the landscape, pH, nutrients to be sure. The texture, actual texture of the rocks has something to do and is carried out into the texture of the soils that become that come out of those rocks or become, modified to become soils. Okay, keep going here. Parent material. This is actually in Southern California in the 29 Palms area, Joshua Tree National Monument around. Here's a fairly massive rock. It looks like it's been eroded. Yes, indeed it has. And that erosion product is scattered here on the desert floor around it. Okay, if you look at the Joshua trees and the creosote, you're beginning to see some way that these plants, and I'm going to go back on that for a second. You don't see many plants growing on that rock. You see a lot growing on the rock products. And that product from rocks is a weathering product. That is to say, it comes somehow, those big massive boulders become small grains of sand or even smaller silts and clays. And by the way, those materials become the substrate for growing plants, including Joshua trees and for that matter, critters, in the landscape around it. You can make some big assumptions there, and you don't have to, but here's really, when you get right down to it, there is something that has to do with the plants and the rock interaction that improves that weathering or accelerates that weathering process. Keep going here. One of the other things at a little bit different scale from the tree roots you just saw is the lichen weathering of rocks. On most of those rocks, even in the most arid climates, or maybe especially in the most arid climates, you actually get a cover of a plant association called a lichen with the rock surface. And it turns out that these are critical players in the weathering of that rock surface, particularly in more arid climates, because that's without much rainfall. Here, this doesn't represent a climate necessarily that has never seen rain. This is the Chiricahua National Monument. And these lichens I just showed you came from, you can actually see on the surface of many of these rocks. Those lichens are, with their roots in organic acids and other factors, including insulation factors from temperature, et cetera, are actually creating a good milieu to change this rock to 1 grain of sand, and then release it into the system somewhere else, or to be deposited somewhere else. Sometimes there's another factor that goes in here, and that's the erosion process itself, illustrated here by sandstorm, basically, or a dust storm in the San Joaquin Delta, which has a lot of soil that's available for wind transport. In most of the arid West, not so much in the East, but certainly in the arid West, where you actually have bare landscapes where soil particles, dust in particular, or dust-sized particles, which are silt particles basically, are available for transport. The wind actually does a huge amount of work on moving that material around in the landscape. Sometimes that material has to come to rest. And the coming to rest of silt particles from dust storms, from clay particles from actually accumulating in water bodies and settling out, or sand particles, which actually don't provide much substance to the dust storms, because the sand actually bounces across the surface when it moves. But in the same way that water moves these weathered particles around in the landscape, wind moves these sedimentary particles around in the landscape, these weathered particles. And all of them have to come to rest sometime. We'll get into that. Okay, I spent quite a bit of time in Peru working in the shadow of near the town of Ica on the very arid west coast of Peru, growing asparagus. And it turns out that so much of that arid landscape, and arid, I'm saying, you know, they get an inch every 12 years or something like that. It's really minimal rainfall in the shadow of the Andes. Provides a lot of dunes. And this particular dune is one of the 11 tallest dunes in South America that I've heard about. Everybody wants to claim the tallest dune. But nevertheless, it turns out if you have a flat piece of ground that's formed of this, basically this dune material, and you add water to it, you can actually grow pretty good crops. In fact, excellent crops. And I've spent a lot of time getting material, asparagus, some tomatoes, mangoes, and other things out of Peru back in the day. This accumulation, this sand accumulation is an interesting, we see dunes all over New Mexico, all over Texas, all over, I shouldn't say all over, but in many places in Texas, Colorado, Arizona, California. These are native landforms that form when sand gets picked up and saltated, jumping across the surface in strong winds and accumulating when the wind velocity dries or drops. Therefore, you actually get these big dune formations. It's fun to think about how dynamic this particular landscape is. You can actually stabilize the landscape, as these trees do, or as this agricultural field does, with vegetation. But there's not much vegetation up here, and it's so arid that you don't get much vegetation. So you actually have a very dynamic, unstable landscape in part of this ecosystem, and a very also dynamic but very stable landscape in another part of this ecosystem. The climatic effects, here's a rainstorm sweeping across a sort of an interior, the Sunflower Valley in the lower San Joaquin, in the Coast Range next to the lower San Joaquin. These rainstorms, all of you have seen the rainstorms coming through New Mexico. You're probably looking at snow now, if I'm not mistaken, over most of the place. But nevertheless, these rainstorms provide very intense deliveries of water. And the water is really one of the more critical agents of the climate that we need to be concerned with. I've already mentioned wind, which has an erosive effect, especially when it picks up other particles and grates everything down. But you also got water coming into the landscape, mostly in the form of precipitation, either snow or rain. But in any case, in California, we depend on these rainstorms especially for this time of year. This is when we get the rains and the moist winters, and this is when we get our snow, and this is when we can actually bank our water up in the Sierra for irrigation in the valley, the Sacramento Valley below, Sacramento San Joaquin Valley. Many similar situations in the arid West, all over the arid West, Colorado, New Mexico. I don't have to tell you guys who live in New Mexico about that. That water from those storms and those precipitation events makes its way to the surface, or it accumulates and stays on the surface and moves out. This is Bernie Falls in Northern California. These waters are being released from stored waters in the volcanic tablelands above this, in this watershed, above these falls. That water, I don't know if you've thought about it, but have you ever thought about what the purpose of a river is? Purpose of a river, yes, it's to move water, but it's more to move sediment. And that water is the power in this landscape that moves material from one place in the landscape to another. And usually it takes it away from one place and stores it in another, which is called a stream bank. Well, that's what we do with our money, isn't it? We take it from one place and put it in the bank. The same thing a stream does. I'll point that out. This is water flowing out of an Oregon soil profile following during snowmelt. In other words, there's upslope from this was a big snowmelt, a big snow bank, melting slowly in the spring, flowing down through the pores that Holly discussed very well, the pores in the soil that allow water to move from one place in it to another. Water accumulates, sorry. I have a very sensitive screen, I think, to this stuff. Let me go back. Water accumulates in that soil profile, percolates down. Water likes to move down. It doesn't like to move laterally until it's actually forced when it hits a barrier, such as this one. This is in San Luis Obispo County. And this is a very friable soil profile that is a very loose accumulation of soil. It's a sedimentary trap for material that's moved in on top of a rock lithic substrate. And at that junction is where one would expect water falling and going through the soil profile, hits that rock, begins to move laterally. And by the way, trees do the same thing, and we'll bring that up later on. here this is a stream, Lower Berryessa Creek, actually, in the town of Milpitas, but you'll have many analogs all over New Mexico and Arizona and Colorado as well, and Texas. You have a very dense substrate here, and you've cut with a backhoe to expose what's above it, which is actually still wet. And this material is not rock. This is a heavy clay. This is let's say a silty clay loam. It has a lot more porosity and a lot more ability to transmit water when that water is actually being transmitted through the profile, hits that restriction zone, and it begins to move laterally, okay? In fact, you're not gonna get much groundwater recharge from this system. In other words, you're not gonna get water being forcing its way through that big, heavy clay layer. Very common system, arrangement, let's say, in riparian systems all over the West, all over the US, all over the world, okay? And one begins to understand a little bit about the dynamics of water movement in the soil by looking at the soils, okay? Those waters gradually collect into streams. This is Cottonwood Creek in the northern San Joaquin Valley, Sacramento Valley in California. But I should point out, sorry, keep jumping. I should point out that this particular stream has been insulted by gravel mining pretty roundly for many, many years, for a couple of hundred years, or at least 100 years in California. Gravel mining and gold mining. And we begin to see some of the characteristics of streams that have had a lot of their sediment supply removed. So again, if I'm talking about the movement of sediment, that's one of the functions of streams. It's one of the things rivers do. And I think it's important to kind of begin to understand that this particular band in here is also, it's not just a band of removal, that is a zone of removal of material, it's also a zone of deposits of materials, and we'll see that again in a few minutes. Can you look at this slide and tell me where the riparian zone is? Okay, this is in some arid hill land south of, in the Bakersfield area, let's say, in California. You see an upland, which is probably an old alluvial fan surface at the base of these hill slopes, another landform, okay? And you see actually coming out of this little drainage, you'll see a little alluvial fan there. You'll see another one up here if I'd taken a broader picture. You actually see a sagebrush community in here and an annual grass, dry annual grasses, but you also see the riparian zone in here. Sometimes it's hard to identify that riparian zone just from vegetational characteristics. In this case, not so much. Also, it's hard sometimes to determine where the riparian zone is just on the basis of where the cut in the stream is. And in this case, not so much. But my point simply here is that all of a sudden, in my assessment of these landscapes, I'm beginning to see a segmentation of the landscape by soil and soil surface, or by soil and landform, that tells me that there's going to be a difference between things on this slope, or this slope, or this fan, or this fan, sorry, or this fan, or down into the riparian cut, down into the riparian. Here's cottonwoods growing in a sagebrush landscape. Not an unusual situation in New Mexico, Arizona, Colorado, arid West, Texas, et cetera. And certainly in California, another member of that arid land suite of states. Okay. Every now and then, those streams get out of bounds. This is the city of Marysville in the Central Valley of California, surrounded by the 1955 Christmas storm. And that water basically cut off the city. Actually, there were floodings all over California, particularly in the Central Valley at that time. New Mexico gets its experience with floods, and I've seen some of the effects of that. But nevertheless, the power of that water in flood is what actually does the mega movement, the magnitudinous movement of materials around in this landscape, these landscapes. And again, remember, the material carried by these storms, by these storm floods, by the flooding waters themselves, material entrained in those waters is picked up somewhere and then deposited somewhere else. It may, in this case, who knows, it may have made its way all the way out through the Golden Gate into the Pacific. But nevertheless, there are downstream effects of these upstream dynamics. And it's something just to remind ourselves, everybody knows that water runs downhill, et cetera, et cetera. Sometimes, this is in the Redding area in Northern California, sometimes those streams will actually start depositing their sediments in banks. Okay, here's a gravel bank. All right, and if you, actually I was taking a picture of this to look, because there were salmon moving upstream. Here's the Sacramento River back here. This is Battle Creek, the mouth of Battle Creek in Northern California, Northern Central Valley. There were salmon migrating upstream at the time of year when this photo was taken. But I was interested in these gravel banks because they are, first, they're an economic resource, yes. They are a sedimentary supply for other parts of the system. They are a representation of dynamics that, again, as a soil scientist and as a landscapologist, we're trying to understand. So keep going. Here's what some of those gravels and cobbles look like. This happens to be in Eugene, Oregon at a gravel pit. But nevertheless, you can actually see the rounded edges on these cobbles representing some form of some long-term transport and finally deposit. Notice all the fine materials around this. That's the weathering product of many of these rocks. You see actually that some rocks don't weather. They don't have a weathering rind like some rocks do. This material in this rock is different from the material in this rock, okay? So we also begin to understand it takes a while to move these rounded, what at one time were probably square pieces of rock or angular pieces of rock downstream and knock the edges off. And that there's a couple of things going on here. One is there's an actual abrasion that leads to the weathering and fine particle development. Another is there's a difference in the chemical constituencies of these rocks, making them resistant or less resistant to some of the temperature and chemical factors that they encounter in their journey. So another further downstream, here's another example of a weathering rind on a huge, this is a buried soil scientist right here, this hat. Anyway, there's a huge gravel, okay, if you will, a boulder with a weathering rind that actually says something's transforming this. It's biologic, it's chemical, and it's heat and temperature, or heat, or the temperature changes. All right. Some of you may recognize this fuzzy picture. I'm sorry, these slides are a little fuzzy. They probably have been expanded, enlarged too much, but nevertheless, this is the Snake River Valley in Idaho, actually at Birds of Prey National Monument or National Refuge. In any event, this particular Snake River stream is occupying a huge valley. That particular issue right there, the size of the stream relative to the size of the valley it occupies, gives you an idea of not just what's going on with that stream at the time, but what has happened in the past. The Snake River Birds of Prey zone sits somewhat above, just upstream from a narrowing in the valley, which has been taken advantage of by the railroads in the past, where this stream necks down. And in some of the enormous Pleistocene floods that traveled the Snake River, this particular little pinch point was just at the head of an opening in a valley or a canyon. And the material coming down here before the bridge was built was carrying some pretty big gravels. And those gravels from this particular point, as the water velocity slows, the ability for the water, to carry sediment decreases. And so the larger gravels sort out, smaller gravels continue to move downstream, particles, et cetera. Well, here's the gravels from this system. My friend Brad's kitchen is about the size of one of these gravels, and this happened to be a 9-mile gravel bar. All right, sorry. A 9-mile gravel bar of big boulders. Look at the characteristics of that rock that Brad has his hand on. It's rounded. It's got a different weathering pattern across it. It's surrounded by particles of different sizes, some as big as Brad's shin, or diameter of Brad's shin, some bigger and some larger and even more larger. And if you go to this particular part in central or southern Idaho, this particular park, you actually see that it's a kind of a magic place, and other people thought so too. Now I'm going to leave that for a minute, and we'll get into some of the more discussions of sedimentary stuff in a few minutes. The biologic activity that is one of those factors of soil formation that we talked about. Biologic activity can take many shapes. Here's one. This guy or gal, probably. I'm going to guess it's a gal. I don't know. I can't see. In any event, there's a pretty good soil forming factor right here at the base of those those stumpy legs. Okay, and that is manifested here in Hong Kong in a marsh. This is a marsh that's been trampled to a great extent by free roaming buffalo, water buffalo, which are allowed to roam free in this special administrative region of Hong Kong. And that's another story in itself. But it turns out the reason I show this slide is that particular marsh impact and disturbance has provided excellent habitat for a rare species, the greater painted snipe, which in 120 years ago was hunted almost to extinction by the English overlords, the British overlords of Hong Kong. In any event, as far as this part in the whole soil farming process, think about the compaction, think about the making available to transport those materials that had accumulated in this marsh. Think about the vegetation that takes advantage of these particular different features, these different patterns in this landscape, making it a home for an endangered species, for a sacred species, the water buffalo, for various farming activities. They raise bloodworms here. They raise all kinds of material that I don't think I'd ever eat, but they have them in the market. I can tell you more about it if you ask sometime. There's a little more subtle biological component. Many of you would never have seen this, but this is what's called a fairy ring. This circular profusion of dryland grasses, again, this is in California, are associated with a fungal growth pattern that allows fungus to grow out from a from a one point source, and actually begin mining the soil for nutrients to the point where the grasses take advantage of it. The fungus is actually providing a different soil moisture status, a different phosphorus in particular availability, and others. But in any event, those fungi, the macrobiota of the soil, are extremely important in moving nutrients around, in affecting water moisture supply or soil moisture status. Again, I could go on and on about biologic effects on soils, but we get that idea. If you look up the Columbia River let's see, this was probably in December, a couple of years ago, you're seeing a landscape that actually nobody saw before. At one point, about 9,000 years ago, a fellow, Kennewick man, so-called, paddled up this river. He had a touring kit that included things that were very Asian in origin, probably Japanese. This is in the state of Washington. Well, what I'm trying to illustrate here, perhaps, so you get it, is the time factor in some of our understandings of soil forming factors. As he paddled upriver, at some point he was either done away with or did away with himself. But nevertheless, when he came into this canyon, there was something going on that we need to understand fully. This is about, let's say it's 9,000 or 10,000 years ago. But about this time that people came onto this continent, by all good accounts, and there's a lot of controversy over this, but nevertheless, by the time when the people came onto this continent for the first time presumably from the Asian steppes and Siberia across the land bridge, my opinion is they probably came paddling along the coast, around the glaciers, instead of trying to walk through the glacier fields. But nevertheless, the key thing is that so much of the water on the whole surface of the earth was tied up in glaciers. And the sea level was about 400 feet then lower than it is now. In other words, this Columbia River Gorge, the surface of the water you see right in front in the background there was 400 feet lower than it is now. The people who came on along the coast saw a completely different coast than we see now in California, Washington, Oregon, Alaska. In other words, the sea level, here's the current coastline right here where the dark is, but the green is the old coastline at the time of the Pleistocene. And the mouth of in this case, the Sacramento-San Joaquin River is about 400 feet lower then than it is now. My point about this simply is that first, there's a time issue in our landscape formation. And second, there is a very definite relationship between the geomorphology that we perceive now and what was going on at that time. And I think what the important part of this is that the point I want to make is that the landscape you're looking at, even today compared to yesterday, is different. I mean, we're getting a little rain. I can look out my window right now and see the rain. That rain is beginning all this process that I've just been talking about, all these processes to move stuff around in the landscape. There was a lot of stuff going on dynamically, weather-wise, climatically, back in the day when people first came onto the landscape. And what I find intriguing is that, generally speaking, if what I think and others think is that the people who came onto the continent first were mariners, they were puddle jumping, more or less, hopscotching from river mouth to creek mouth to river mouth along the coast. They were well adapted to foraging for marine resources. Their campsites were not up where we are today. They were 400 feet lower along the coastline. This is illustrated many times, many ways, and I love talking about this because when we start talking about soil formation, the magnitude of time is hard to understand, but once you kind of get these parameters for understanding it, 20,000 years is pretty good time for soil formation for modern Holocene soils, that is soils of the last 20 or 30,000 years. Well, in any event, that's one time scale. In the Madison River Valley, I'm looking out across the Madison River in Wyoming. I'm standing on a terrace, and you can see in the background here, terraces. There actually are 11 terraces here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, anyway, 10 or 11 terraces, matched terraces. This is below Earthquake Lake, which comes out of Yellowstone. In this landscape, time is kind of an interesting concept. The youngest materials here, the youngest landscape here, is down here at the bottom. These are the materials that have become sediments, that have become soils, that are terraces, now being dissected again by the stream as the stream continues to move down, leaving behind their floodplain in each case to create a flight of terraces. All right, and again, what's the time scale here? Younger to older. Generally in geology, you think, well, you go deeper, you get older. Here you go deeper in this system, this inset system, and you get younger. Okay, so you got old soils up here. Now, wouldn't you imagine that an old soil that's been in that landscape for quite a while has actually different characteristics, particularly since it's been exposed to longer leaching time, moving materials out of it, longer accumulation time of deposited aeolian wind deposited materials. It's going to have a completely different characteristic because it's been in the landscape longer since it was deposited out and cut through, then the next one down, then the next one down, then the next one down. Again, looking at these ecological processes and the dynamics, one begins to understand why we see such diversity in soils. And I'm not going to get to show you all the diversity, I don't get with it. Here's a result of a 5-inch rainstorm in 24 hours back in, can't see my date, back in the 90s, I believe, early 90s. This is in wine country in the Central California wine region near Templeton and Paso Robles, California. But in any event, this particular plowed landscape, not yet planted to grapes up here, got 5 inches of rain in 24 hours. All right, that's a smidgen of rain when you compare it to 20,000 years, okay, for sure. Well, in any event, that rainstorm sent a lot of material, but surface flow of waters carrying those sediments downstream into my neighbor's, my friend's orchard, or excuse me, his vineyard. And here are the deposits that actually filled up this little stream, this little pond over here, inundated the base of this oak, came right through his newly planted vineyard, including burying the drip lines, burying the grapevines. That's a 16-inch bit on that spade. And in this one event, this kind of material was moved into this whole system, and it had not experienced this before. It had been perhaps a higher landscape in the past and been solely and simply removed as well. But nevertheless, the magnitude of this in 24 hours, 5 inches of rain, the magnitude is astounding. And this is a minor storm, relatively speaking. We get them all the time here. When we're lucky, we get rain. And nevertheless, the materials that moved down varied from very coarse to very fine. Here you actually see the fine deposits as the stream was actually losing velocity. The finer material began to settle out, and actually the top of this system is graded to finer materials from the bottom, which has coarser materials. So understanding that and understanding time and dynamics and stability in this landscape, that was an unstable landscape that was exposed to this particular rainstorm. And the result was pretty significant from the standpoint of Bonnie Doon Vineyards at the time. Okay. One of the things that Holly covered really well was salts. Here is an accumulation of salts on the surface. It's an aerial photo of salts in alfalfa fields. They're trying to plant alfalfa. You can actually see agricultural tracks across this. But the salty soils actually have a big effect on the vegetation that grows in them. Here in Utah, south of Salt Lake City in the Utah Lake Valley region, one sees huge accumulations of salts. These are not good for plants. There are very few plants, a few, that actually can grow in these accumulated salts. These are interior basins that have a huge evaporite component for their salts. I'm trying to check my time. Okay, I'm keep going here. But salts are really hard on plants. And as Holly mentioned, they create drought-like conditions. They actually draw the water or encourage the water to leave plants, plant roots. Only certain adaptations by plants can actually make this system a living system. Salts accumulate not only on the surface, but also this is actually in the Ica, Peru, an accumulation of salts at a hydraulic barrier in the soil profile. Again, right in the central part is where water hangs up and begins to evaporate and leave salts behind. Okay, I'm going to race through the rest of these. I've mentioned all those factors. Now I'm going to get a little bit more to the practical side of things. Again, a few things that I will remind you of as I go through this. One is, here's a landscape in the Central Valley of California, very similar to some of the meandering rivers of the Midwest, of Texas, certainly of New Mexico, in your broader valleys, in the Rift Zone, et cetera, et cetera. This particular landscape shows some interesting stuff. Among other things, Oxbow Lakes, the meandering nature of the streams. Here's an Oxbow Lake. This was a loop of the river or the stream that had been cut off in some sort of event, probably a flooding event, and left several of these Oxbow Lakes on a very low gradient stream system. If you actually remove all that disguising vegetation there, here again from the air is traces of old streams showing the diversity of soils just across one planting field. Imagine you're a farmer trying to irrigate this field for your alfalfa or corn or sugar beet crop, and you go from one side of the field to the other. You're actually going to see, count them. You can start anywhere and you can count 1, 2, 3, 4. Here again in the central, in Nevada, across the border into Nevada from California through one of the mountain passes, you see a riverside field showing an extreme diversity of soil types. Assume that the tan streaks in here are sands, and the darker streaks are finer materials, probably a little more organic. But again, this is, if you're trying to make irrigation decisions about this, arboricultural decisions, orchard decisions, how do you irrigate this? How do you provide water to those plants if you got a sandy soil on the one hand, 10 feet later you've got a silty soil, and 10 feet later you got further along, you've got a clay soil. Well, one can look at the landscape, one can look at the soil landscape and begin to make some decisions about this. Mother Nature does the same thing. Here's one of those interior valleys, actually bounded by glacial moraines in the Sierra. Look at the vegetational complex here associated with stream channels. You see everything from conifers to sagebrush growing side by side. If you don't get an idea of diversity just looking at the valley floor, look at the slopes above it. Look at the difference in where trees can grow and where they can't grow. Look at the difference in where sagebrush can grow and where it can't grow. Not only do you get this diversity across the landscape, you get it into the landscape. Here's a gravel pit, actually near my home, about 15 miles from where I'm sitting right at the moment. You see this is an exposure of a gravel mine in a gravel mine that shows different episodes of landscape formation from the top, which is the most modern, to this older, finer texture material at the bottom. At some point, hydrology of the stream changed, or sediment supply to that stream changed when these things were being deposited, and these lenses were being deposited. This has to do with that stratification I was talking about earlier. Most of these sedimentary systems in New Mexico and Arizona, as well as all of California and Texas, most of these systems are highly stratified by texture in particular. This is a textural difference in the sort of the brownish material here in the center versus the cobbly and gravelly materials above it and below it. You actually begin to see here little talus slopes and alluvial fans from material that's moved down slope. Okay, all right. Here's a soil profile. And I don't think you'll find many soil profiles that differ from this anywhere, as long as you've got a little bit of time in the landscape. This is on a fairly stable alluvial fan in Bear Valley, somewhat north of where I'm sitting right now. But I've seen the same exposures in deeper soils of Arizona, New Mexico, and places I've worked, and in Texas. You see here, you see a dark accumulation. It's not a different material between the textural material from here to here. The texture of the soils differs a little bit. There's some stratification, there's some gravel zones in here, but in general, it's about the same. It's a silty loam, and it's got a dark color here and a gray color here. Of course, that's the A horizon, which is characterized by high biologic activity. A lot of organic matter is going in through the grasses and forbs with their roots. If you want to move material into a landscape, if you want to move organic material into your landscape, whether you're an arborist or an orchardist, try growing plants. Try letting the plants do the work of putting the carbohydrates down into the soil. That's called carbon sequestration. We can get into that, but nevertheless, here, if I were to, I'm taking this from one bank and looking at the other. If I go to stand on that bank and look across the valley from where I just took the photo, I'm beginning to see the same features I've shown you, and I'll show you when I'm in New Mexico with you at our workshop sometime. I'll show you the same features in every stream. You get small terraces along the stream. You get a little bit higher terraces, which represent a different flooding regime and a different base level of the stream. You get alluvial fans. Here in the background, you see alluvial fans up in here coming off the slopes. You get a different vegetation component, whether you're here, next to the stream, on the next terrace, on the valley in between. This is sort of an alluvial fan this stream is cutting through and actually has formed. So here's an alluvial fan that has a different vegetation component, and then you get up into the forested up there. Again, I've segmented this landscape so well that I can walk to any part of this and say, what do I expect soil moisture status to be? What do I expect nutrient status to be? Where am I going to get the most dynamic erosional activity? Where is it going to be most stable? Reading this landscape, it's pretty difficult sometimes in urban situations. And we've all done plenty of that, but reading it is a little difficult, but it's fun. Just to show you the complexity of soils, this is obviously the Four Corners states, more or less, and New Mexico, Arizona, Colorado, Utah, etc. This is a soils map. At some point, somebody's decided that all of this diversity has to be mapped. It has to be put somewhere. If we're going to be using these landscapes, we need to know how to utilize them and how to make decisions about what we do with them. Some of that's intuitive. Some of it we just really have to deal with. These soil units, this is in very southeastern corner of Arizona, southwestern corner of New Mexico. The town of Portal is right here. This is a soil map that's available on the web from the U.S. Natural Resources Conservation Service, USDA Natural Resources Conservation Service online. You see these orange lines, which don't come out too well, it looks like here, but nevertheless, you see the orange lines, they're indicating different soil units. And this is an alluvial fan that comes out of the little creek coming out of the Chiricahuas. These are all, many of these are planted now to, I noticed last trip, pecans and perhaps other nut trees. Amazing agriculture going on in this arid corner of the Southwest. Here's what those units look like, again, in the central coast of California near Half Moon Bay. Those units, these TE, for example, TEE2, GBF2, TUD2, et cetera. Those units, those polygons have soils that have similar characteristics. And you'll find that there's some relationship between landform, in particular streams, slopes, alluvial fans throughout. So I'm suggesting that you might want to take a look at your soil survey reports from the USDA Natural Resources Conservation Service if you're asking questions about soils. This particular map I just like. The reason I like it is soils have color. This map of the US was made from surface soil colors from every soil resource unit across the United States. And there's a huge amount of soils information here just in the color. I don't have time to go into that. But if you think soils aren't pretty, look up Hikaru Dorodongo sometime. It's a Japanese art form where you actually take clay of different color and work it into these spheres called shiny dumplings in Japanese. But the colors are characteristic of various properties and qualities of those soils. And again, some of that's available to you, the knowledge is available to you from the soil survey reports. Some of it you already know. Some of it you know that a red soil probably has rusty iron in it, for example. If you look, and here I'm working on a recycled water project, application recycled water in the Santa Clara Valley. And the woman standing there, by the way, some of you may know Nelda Matheny. We had several projects together. Among them, we're looking at soil units in places like city parks. And here are the tools of the soil scientist, a Montana sharpshooter, the red spade, an auger, a 4-inch auger, 6 foot long. And here's what we pulled out of this one hole. I think I've got another photo. Yes, this is what the soils look like in that particular place, laid out on my tarp. Here's the bottom, here's the top. Now, if you want to read this, if you want to read the history of this landscape, start understanding this soil you're going to get a feeling for what's going on in that particular site. Maybe different 10 feet away, but nevertheless, in that particular site, we've got a huge organic matter accumulation at the top. We've got some really impoverished soils at the bottom, and in fact, probably sedimentary marine sediments and everything in between. And those of you who have never dug a soil pit, I like doing with backhoes more than I do with augers. I spent a lot of time working on my shoulder strength with augers, but nevertheless, you can do this virtually anywhere. I think even Holly showed a couple of slides of similar stuff. But it's not just an exercise in finding the constraints in the soil. Certainly that's part of it, but it's also finding the history of that soil, or history as a soil's pedon, a unit would look at, you'd see. And we go ahead and we can get dimensions on those. We can label them based on their characteristics. We eventually come up with a soil map. I'm going to race through now a couple of, boy, somebody wants to interrupt me and tell me I need to stop, you can tell me, but here's a project in the Central Valley. I have a tomato field here. I need to turn it to a wetland. It's one of my projects. This was the one that was mentioned at first about the biggest wetland mitigation project in the Western US, or west of the Mississippi at the time it was done. This tomato field is going to become a wetland. Some of the best soils in the world becoming a wetland, and don't know that I understand that. What was happening was there were impacts to wetlands in the town of West Sacramento and Yolo County in California. We took a look from the air at what the river, this is the Sacramento River, was doing. I showed you a few oxbows. This is an oxbow in formation. Sacramento River is pretty well tamed by project levees of the Corps of Engineers, but nevertheless, we looked at up and down the river at these systems, and we found that there were plenty of oxbows that had been actually more or less abandoned and actually make pretty good wetlands. They hold water. The water in the bottom is tied to the water table. So we did some surveys. I did some surveys. I found the IOU pools there, IOU oxbows. But anyway, we designed a restoration project to take advantage of the water table in that tomato field I showed you. If you'll remember the barn in that field, we dug that oxbow. We had done a huge amount of, I'd done myself about 150 soil pits with backhoes, trying to assess the transient water table to find out how deep we had to dig in order to get to the water and actually create a wetland. And turned out it was about 16 feet below the surface level. I would love to spend more time talking about it. Don't have much time. Nevertheless, there's that barn again. We've put our oaks in. We put in this big oak at the very up top left there was one of the native oaks providing much of the seed, the acorn seed for new oaks. We put in we assayed all of those Oxbow Lakes for their vegetational components and zonation, et cetera. Again, more time, I'd talk to you in more depth about it. Here's what it looks like from an NRCS web soil survey download. The uppermost Oxbow Lake is the one I was just showing you. The Corps of Engineers also did mitigation, created another Oxbow down below in that second yellow polygon. Nevertheless, big project, planting trees. I don't know the number of trees there. I worked on the Apple campus and we planted about 9,000 trees there in Cupertino. This one probably doubled or tripled that number, and a lot of it was transplants, but a lot of it was acorns as well, and other seed crops. How are we doing, Marisa?
Well, I think we do have a couple questions and we have a couple raised hands. So let's, I know you have a lot more to share. We do really appreciate your offer to come visit in person. And so maybe save some of the rest for when we do that.
Absolutely. And, I could just race through these slides and just, you'll see some pictures.
Yeah, Jordan, if you'd like to start with the questions, that'd be great.
Fires, I want to talk about fires at some point, but fires are very destructive to soils. There's my accountant looking for my tax records and the remains of his home in the Oakland Hills. This is what the soil does. It fires just like a clay bed. Sometimes those stay in the soil a long time. Here's the Apple campus when it was Hewlett Packard. Now it's Apple. And here's some of the work that we did there. Compacted soils. We did a lot of work on trying to disrupt that compaction with big tools and small. We can skip that. Here we get into the Arizona durapans that are actually some of those restricted zones. Caliches. That's about it. I could go on and on. Sorry, I kind of slowed down on some of this stuff, but last thing I'll say before I answer questions, I want to communicate to you how excited I am about soil science, because this is the story. These are the stories that we actually get out of soils. And in spite of the excellent lecture that Holly gave, I'm not a numbers guy. I'm a story guy. And that's what I've tried to show you. So I'll leave it at that.
Thank you.
Questions?
All right. I'm gonna bring up the first question that was actually a question I wrote, but a lot of other people seem to have the same question, and it gets into people more than soil. But the question is, what advice do you have for folks like us who are trying to convince people higher up in whatever kind of administrative system we might be in that nuanced differences in soils matter when you're dealing with planting and maintaining trees and other components of an urban forest? My reaction when I brought up nuanced differences was I was told that we don't do nuance. Well, okay, but the trees do. And
yeah,
how do you approach that level of resistance?
You know, there's a hard way and an easy way. The easy way, think trees. You know, why not? That's the theme of the conference, and the theme of you have to think like a tree. You can't get an engineer to do that to save your life. And God love my good friends of engineers, but I do have those tensions are really important. It does take sort of what you've just gotten for the last hour from me is an explanation to them, but you don't have those hours. The best way to renovate this site is to grow alfalfa on it for 3 years before you ever come in with your bulldozer. It's hard to get that across. However, there are good results and bad results, and I have a collection of failures that I like to show engineers and others who actually are fighting for their, I hate to say it, piece of turf themselves. They have their own approaches. The worst part is, the hardest part is trying to compromise on either side so that you get sort of what you want. We have an engineering fix of about 30 years. If anything is over 30 years, it's probably time to be replaced. Hewlett Packard at Apple, for example, was a 30-year-old campus, and I was digging holes to create what you saw partly in the slide. My point simply is that it does take an educational effort, and you're not going to depend on somebody's background to understand that. You need to go a little bit slowly and try to communicate that diversity issue. The best advice is you be educated yourself and understand all of those things that I was talking about, stratification and compaction and root development, and argue, but that's the best I can do, is just be educated yourself. That's the critical component of the soil assessment approach that gives you a decision tree that you can then convince people with. So there's an educational component, there's a convincing component, and there's everything else.
Yeah. Another quick question, and probably about all we have time for, but this one had a few people interested in it as well. Some desert sandstorms carry disease organisms, some known as valley fever. Are there certain soil formations that carry these organisms, and should people be aware of that?
Breathing dust is no good. You don't like to breathe dust, because when you breathe dust, you're breathing silt-sized particles, small particles that actually can accumulate and the body's hard to get rid of. And that's without even regard to its biology. The valley fever issue has killed a lot of farmers and soil scientists in California. Valley fever is a fungal disease that whose spores reside in the soil for a long time, and the inhalation of them we're getting good training during the pandemic. I have my mask right here in my pocket. If you're working in these systems, particularly in arid systems with a known valley fever or other, I hesitate to get into the scientific names of these disease organisms, but a mask is good advice. And it's particularly important for really big dust producing activities like orchard management and soil pits.
Cool. I guess I'm going to turn it back over to you, Marisa. I think it's time to wrap this up and give away a chainsaw. David, thank you so much for your excellent presentation. I'm a fan of soils, and it's really hard to kind of get people to see the complexity of it. They look at it as one uniform thing of dirt, and it's not.
Yeah, well, I've taught a lot of classes, soils for engineers, soils for agriculturists. It's fun to do, and it's fun to see people's eyes light up sometimes with soils. And when you get to that point, then you've satisfied some of those tensions you talked about. So my pleasure.
Thank you very much, sir.
Yeah.
Marisa, it's all of you.
All right. Yes, thank you very much. Thank you, David. Kelly, thank you, Joran Veers. Thanks all the behind the scenes people. I do have a couple more slides to share. And so if I'm getting ready to take down this CEU slide, but if you didn't have a chance to catch it just now somehow, you can go back and view all of the presentations within Whova, and you can speed to the back, speed to the front. You should also watch the content if you didn't, and catch the CEU codes. So that is another way for you to get them. So thank you for that. And I'll start sharing this next. Dun, dun, dun. For our closing remarks today, we are excited to talk about our sweepstakes. So let's see, I'm sharing my screen. Okay, so usually there's somebody who's doing like a drum roll, you remember, and this is a chance for us to really celebrate the end of the conference and thank everybody for participating. I, of course, will also want to thank all of our sponsors again. Thank you so much for participating every year that we have the conference, but especially this year in the virtual format. We were really pleased that everybody was still willing to participate, and all of you also are willing to attend the online conference. Thank you for that. And thank you to all of our speakers. I also want to thank the board. So we have hosted this conference, well, not me, but the board collectively with different members over the years has hosted this conference since 1986. With an all-volunteer board of committed tree industry members and supporters. So thank you to our board and board members, and thank you also to all of our friends of the board. And so I have some of those listed at the bottom. Yeah, and really working with this team is very fun, and you can imagine, I cover urban horticulture, and so I get to work also with roses and also with bulbs and tomatoes, but the tree people are the best. I think we all know that. And we can't have George Duda give the sweepstakes away, the chainsaw away with his hat. So I asked last night if he had any photos to share, and so he sent me this great one. And I think a lot of you have been there before when George puts the hat on and he's selling the raffle tickets, and it's been really fun. And we're sorry we can't do that this year. I also happened to look up how much it costs to buy these hats, or could I find them online? And George, you should hold on to yours because on eBay, they're selling now for like $150 a pop. So now these foam chainsaws are a collector's item. And I also reached out to a friend who works with the Roswell City Parks and Trees there, and he had this image of George wearing the same hat at one of his events for Arbor Day in 2018. So we're sorry we can't host the live conference again this year, but we do have the chainsaw to give away. And so with that, here is our winner. Frank Pond is the winner of our chainsaw this year. Congratulations, everybody gives a clap. And Frank Pond is with Aspen Leaf Landscaping. Thanks so much, to each of the different landscaping companies and teams who signed up their employees to attend the conference this year. We appreciate you and all of you, the other attendees as well. We do have a survey for you to fill out. And again, that really helps us as far as how we plan ahead for future years. Please fill out the survey. And then again, in the very bottom of that survey, you can type in, maybe you have ideas of topics or specific presenters that you've seen elsewhere or that you think could do a really good job. And you can enter that in that final comment box on the survey. I think, unless I get any texts last minute, and so I think that's it. Thank you so much for joining us this year. And we hope to see you out there with the trees. Stay tuned for any live events that we can have in the coming year. Oh, I got one more message. Okay, thumbs up. We're going to sign off now. Thank you again.